Hello, guys. Welcome to Science for this Monday. We are going right on through Unit 4, and we're asking some interesting questions during this chapter. Question number 1 was, what is sound? So we talked the end of last week there about what is sound? What makes sound, and is it travel in waves and things that we've been looking at about sound. I really enjoyed our sound lessons last week, and as we begin this week, we're asking another question. And this question is, what is light? Light is pretty important, isn't it? Without light, you can hardly see me in my classroom. With a light, it lights things up. We can see better. So we know light affects how we see things. What else does light affect? We know it makes plants grow, and we'll talk about how that happens later on in this year. But the big question today is, what is light? And so today we're going to go through this lesson in your book. So get your science book out and open it to page 169. It's hard to believe we've already covered that many pages in this book, but we have. We're on page 169, lesson 3 in unit 4. What is light? So let's dig into the lesson. I'm anxious to see what we're going to learn today. Well, light, energy. We know light's a type of energy, right? Have you ever made shadow figures with your hands? If you have, you've experienced one of the characteristics of light. That's fun, isn't it? Shadows are a part of light. We're going to find out about them. Light is a form of energy that moves in waves and can travel through space. Light waves are transverse waves. As these waves move forward, energy is carried perpendicular to their forward motion, forming an S shape. Light waves spread out in all directions, traveling in straight lines from its source. Light can move through a vacuum because it does not need matter to transmit energy. Now, that's different from sound, isn't it? Do you remember when we talked about sound? There couldn't be any sound in any place where it does not have an atmosphere, like outer space, because there's no air particles for the sound waves to bounce off of. And so sound doesn't travel in a vacuum, but light does. And that's a good thing, because light from the sun has to travel through space to get to us, doesn't it? But light can travel in a vacuum, it said, because it does not need matter to transmit its energy. This is why light can reach Earth from space. Light travels faster than anything else in the universe. Did you know that? Light travels faster than anything else in the universe. It takes only about 8 minutes for light to travel the more than 93 million miles from sun to the earth, from the sun to earth. So 149 million kilometers, 93 million miles from sun to earth. It only takes 8 minutes for the light from the sun to go that far. That's fast, isn't it? Nearly all life on earth depends on energy from sunlight. Let's go to the next page, page 171. Let's look at some other characteristics of light. Shadows form when a solid object blocks light. We learned a little while back that that's called an opaque object, right? As it blocks the light. Light naturally spreads out in all directions as it travels. Light travels in straight lines until it hits the lamp shade. Draw arrows to show how light travels away from the bare bulb in the photo. On the right, draw arrows to show how a shade affects the path of light in the photo on the left. Okay, so we can't draw arrows, but with nothing like this lampshade around it, we read in the last page that it travels out in straight lines in all directions. So every direction from that light bulb, to the left, to the top, to the side, to the right, it travels out in all directions in straight lines. Light does from an this bulb, because it's not covered. Now inside the bulb, inside this lamp, we've got an opaque object, this lampshade, that's bouncing, that it's stopping it. So it's stopping some of the light from coming through, but there's a hole in the top, so light comes out the top and it comes down the bottom, but it stops it from going out to the sides. Okay, let's look at the next page. Now you see it, now you don't. You may think of light as the energy that allows your brain, with the help of your eyes, to perceive the world around you. And yeah, that's what we said. If I turn my light off, it gets dark in here. But there's a lot more to light than that. Most of the wavelengths of light are invisible to our eyes. Do you know that? We can't even see some of the light. Look at this up here. Radio waves can have wavelengths as long as several football fields. Well, that's long. So remember the waves we talked about? The wavelengths. Can you imagine a wavelength as long as a football field? They have a big, long wavelength. Now, wavelength, remember, is the top of a crest to the top of a crest, so from here to here. Night vision instruments use infrared waves to make objects visible in dark settings. Have you ever looked through night vision goggles? They're pretty cool. Wireless phones transmit and receive microwaves, which have some of the longest wavelengths and lowest frequencies in the electromagnetic spectrum. Let's learn some more about light. What's it talking about that we can't see some of it? Light waves are all around us, but many of them are invisible. The electromagnetic spectrum. What is that? Well, it's a range of light waves organized by frequency and wavelength. So if you could arrange, I had a phone call. So the electromagnetic spectrum, if you could take the wavelengths, different things give off different wavelengths, like we were seeing the radio waves and cell phones and different visible light waves, ultraviolet light waves, X-rays, microwaves. They all have different wavelengths and frequencies. Now remember, wavelength is the distance from the top of the crest to the top of the crest. And frequency is how many there are per minute, per second, how many waves there would be per second. So different parts of light have different frequencies and wavelengths. So the electromagnetic spectrum is a range of light waves, and they're organized in like a chart by how long their wavelength is or by how many waves there are in a minute. So it's just a way to organize and categorize wavelengths and of different things. And we'll look at some more of that later. At one end of the spectrum, waves have long wavelengths and low frequencies. So that would be long wavelengths and not many waves per minute. These include infrared waves, microwaves, and radio waves. At the other end, waves have short wavelengths and high frequencies, so not very far from here to here. And there's a lot more in this little space than there is in this space, right? There's just one here. There's like 4 that could fit in here. So this is kind of a picture of these 2 pages here, 172 and 173, of the different kind of electromagnetic wave, how frequent they are and how long their wavelengths are, similar to that. So the more frequent with the shorter wavelengths are ultraviolet rays from the sun and X-rays. They're more intense, aren't they? I guess you could say there's more frequency, higher frequency, and shorter wavelength. So when you get X-ray, if you break your bone or something like this, you're in about this portion of the electromagnetic spectrum. The light that our eyes detect is called visible light. Visible light forms one very narrow section in about the middle of the electromagnetic spectrum. Visible light looks white to our eyes, but it's actually made up of many colors. Red light has the longest wavelength in the visible spectrum, and violet has the shortest. So I don't know if you've ever studied the colors of the rainbow. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. So red has the longest wavelength from here to here. This wavelength, remember? And violet, it's at this end of it, has the shortest. If you ever look at a rainbow, you can find all of these colors from red to violet. Red, orange, yellow, green, blue, indigo, violet. I used to have to memorize that when I was in school, the colors of the rainbow in the right order. And then they're made up of different colors because each color has a different wavelength and a different frequency. But we see light, we see all of these together as white light. Isn't that odd that the light we're looking at, this light that's shining on my face, it's made up of all of these colors, not just white. Isn't that odd? What about laser light? Have you ever played with a laser pointer? Never should point one up at a plane. Never should point one at anybody's eye. But if you ever play with one, they're kind of fun. You can get your dog to chase them like this boy's doing, or your cat chase it on the wall. Lasers have many uses in schools, hospitals, stores, and homes. What exactly is a laser? Why are lasers so important to people in so many different fields? Light from a bulb shines in all directions, we said. But laser light's different. A laser is a beam of light focused in only one direction. Also, a laser beam contains only one wavelength of light. These features make a beam of laser light very precise and powerful. So, let's look at the difference between this light bulb that's shining on me and laser light. It's a beam of light focused only one direction. This light that's shining on me, it's up here, it's down here, it's over here, it's here. It's shining out in every direction. But a laser light shines in only one direction. That's why it goes to a specific point that you pointed at. It's going only one direction. It contains only one wavelength. Remember, this light shining on me contains red, orange, yellow, green, blue, indigo, violet wavelength. It has all the colors of the rainbow in it. And so it has different wavelengths, but a laser beam has only one of those colors, one wavelength. So it makes it very precise and very powerful. If you've watched your mom or watched the cashier ring up your mom's groceries, or if you've used maybe like a Food City card to get gas, you have to put it under a little laser scanner. They read barcodes in stores, and even in the library, if you help Miss Dalton check out a book, she has the little thing that scans your book. It uses lasers. Lasers are very, very important part of light. Artists use lasers to make three-dimensional images called holograms. Some doctors use lasers as cutting tools in surgery. My dad had a little cancerous place, and so the doctor used a laser inside of him and cut that cancerous place out. That's pretty amazing, isn't it? They're so precise that you can use them inside a human body to remove something that shouldn't be there. Lasers are used to cut steel in factories and metal shops. Now that's some powerful light, isn't it? Laser pointers help teachers in classrooms. Police detectives use lasers to analyze fingerprints at crime scenes. In all these cases, lasers must be used safely. You should never look into the source of a laser's light, as it can damage your eyes. There's not a whole lot of CDs anymore, but there's still some DVDs. Lasers read those digital information on CDs and DVDs. It's a laser inside your DVD player that reads the disc. All right, so let's sum up this lesson. You know the trick here. The answers are at the bottom. Why don't you fill that in? What are 3 new things we learned about light today? Well, I had taught it before, but I had forgotten about that electromagnetic spectrum, that different colors of light have different wavelengths. So that was something I learned today. And actually, I'd forgotten that white light that comes from the light bulbs in your room or at your house, they're made up of all different colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. I learned that about light today. I never thought about using a laser to cut metal, to cut steel. That was something interesting I learned today. So light is a powerful thing, isn't it? I also didn't know it just took 8 minutes for light to travel all the way from the sun to Earth, millions of miles. Pretty amazing. So light is interesting. Well, here are, looks like 9 vocabulary words we looked at today. So why don't you do this in your book, page 177? Go ahead and do it. We're going to do one more little lesson. We're going to do the digital lesson on light tomorrow. So I don't have a vocabulary assignment for you today to do, but there will be for you tomorrow. And it will be these 9 words. And as always, do this, make them fit, make sure you got them right, and then use this page to do your vocabulary assignment tomorrow. That's fine with me, because this shows me that you're practicing and learning the words. Okay, so use this page to help you with your assignment. Tomorrow, there'll be a digital lesson on light and then a vocabulary assignment. No assignment today. Okay, let's just look at this together. Explain how light travels. Include as many details as you can. Well, we learned that light travels from a light source in all directions. It travels in straight lines. We saw that light can't travel through an opaque object. It forms a shadow because it blocks the light. What else did we learn? We learned that light travels at different wavelengths and different frequencies. We learned about laser light, that laser light is one frequency and it travels in one direction in a straight line, not in all directions. We learned a lot about light. Describe the part of the electromagnetic spectrum that people can see. Then name 3 devices that use the electromagnetic waves that people can't see. Okay, well, that part of the electromagnetic spectrum that we can see was called visible light. It's what we can see in it. Visible light contains those colors of the rainbow we just talked about: red, orange, yellow, blue, green, indigo, violet. And then 3 devices that use electromagnetic waves people cannot see. X-rays, we can't see X-ray. Microwaves, you don't see waves going through your little microwave oven. You see the result, but you can't see the waves. What else? Radio waves, you can't see radio waves flying through the air, but they are there. This says, circle the light that would be best for pointing out details on a map hanging high on a wall, then explain your choice. All right, looks like we've got a laser pointer, a flashlight, and a spotlight. Well, if you want to point to detail on a map, you want to use this little laser pointer to show exactly what you're talking about. Explain why light produced by the sun reaches Earth, but sound produced by the sun does not. Wow, what a question. Well, it has to do with that atmosphere, doesn't it? Do you remember what we learned? Sound has to have an atmosphere. Sound has to have particles to travel through, and space has no atmosphere, no air. Light does not have to have an atmosphere, particles to travel through. Light can travel through a vacuum where there's no air. So that's the difference, isn't it? Okay, next page. Well, that's our next lesson. So we are done for today. Thank you for being a good listener. And tomorrow we're going to do a digital lesson, and we'll